Hi, everyone. Welcome to our very first UTIG and BEG seminar. And on behalf of the seminar organizers of both UTIG and BEG, I would like to thank many people who make this happen. So this idea of this joint seminar started with Benjamin Beasley's suggestion to the dean. So after one of the default lecture in the department, and Benjamin suggested to Dean Laura, maybe we could have reception after one of our seminars on the Pico campus. So Dean Laura generously agreed to sponsor one reception per semester, and she suggested it would be best if it is a joint seminar by UTIG and BEG. And then the director of UTIG, Damien, and director of BEG, Scott, are both very supportive of this idea. So then we started planning. So the committee members of the seminar committee of UTIG, including John Goff, Tony Reston, Duncan Young, and Daniel Tolman, Nathan Benz, and myself, and also BEG seminar organizers, Nor Scuba and Wang Ping Li, and we sit down together and we plan out the one seminar and invited speakers. And we also got help from our great administrator team, and including both sides, and Rosalind, Phyllis, Dina, Miller, and Jennifer Galavis. Uh, and also not to forget our amazing media expert, Constantino, for advertising this event. And lastly, thank you all for coming here. It's really great to see people from both units sitting in the same room and listen to the seminar that will be presented by Dr. Dessa. We hope this will be a regular event every semester because the dean agreed to sponsor a reception every semester. We hope this will be one of the many mechanisms that strengthen the ties of those units and also the units of the department, 3 units within Jackson School, and also like foster collaboration and communication. And so we hope you enjoy the seminar today. Right. Um, yeah, I think we recorded it. Anything? Okay. So I'm very honored to introduce today's seminar speaker, Clara Desert. So Clara is a senior scientist and also the head of the climate analysis section at the National Center for Atmospheric Research. So Clara received a bachelor's degree in Earth and Planetary Science from MIT and a PhD in atmospheric science from University of Washington. She's a fellow of the AGU and also the American Meteorological Society. And in 2021, Clara was inducted into the National Academy of Science. Congratulations. Um, Clara's research centers on characterizing and understanding the large-scale patterns of climate variability and change using observational data and climate model simulation. And she particularly focused on the role of interaction among the atmosphere, ocean, and sea ice. And over the last decade or so, she has pioneered the use of so-called large ensemble climate model simulation to understand the uncertainty of regional climate change, and which she will talk about today. So in addition to her research, she also spent lots of time helping the climate research community, like leading the community research project and also developing the climate research tools and then like resources like climate data guide for everyone to use. Um, so we are so happy to have you here. I'll stop here and please start your presentation. Well, it's really honor, privilege to be here.
glad that so many of you have come, and I keep this very general talk. Happy to have questions during the talk and certainly after. So thank you all for coming, and thank you for that. Because my postdoc maybe 10 years ago or something. So super proud of okay, so today I'm going to talk about this long title here, to characterize this type of work as a range of outcomes. And I'll start with some eye candy, and then we'll kind of dig into the nitty-gritty of some of this stuff. So really the theme is that we need to consider both natural variability and systemic influence, and we're looking at local and regional trends in climate parameters. Audio is not good, somebody just said that. Sure, I'm happy to. Can I shut this one off? Yeah? Okay. All right. My best. Is this good now on the audio, hopefully? All right, and just let me know, wave your hand if it's not good audio. Yeah, exactly. Okay, much better, thank you. Okay, you guys can't see what I see. All right. Okay, so let's dig in here and see how to advance my slides. Obviously haven't practiced at all. How shall I advance my slides? Yeah, that's what I'm doing. Nothing's happening. All right, technical difficulties. Okay, perfect. Great, thank you. All right, so we're starting with eye candy and starting with something that's super familiar to everyone, which is our day-to-day weather. So you can go to the NOAA regional climate offices, and you can, for any city where you have long data records. So I picked Austin a couple days ago, and this is the time series of the actual observed high and low temperatures for 2023 in that darker green line, and then sort of the range of historical highs and lows over the course of the year. And the point is that there's just so much variability, say in that the red and the blue bars. So a lot, 20 degrees Fahrenheit of, you know, typical range of high temperature and low temperature on any given day. So that's enormous. And then from day to day, as you all have experienced, especially in the spring and autumn seasons, a lot of very high amplitude variability from day to day. So this is what we all know from living here, and just this enormous amount of variability. So now we're going to go to a very different time scale, but the same kind of concept is that there's lots of variability even on longer time scales. So here, this is again eye candy, and we'll come back to these maps a little later in the talk. But this is the projected range of future change in wintertime precipitation over the next 50 years from a single climate model under a single scenario of greenhouse gas increase, the RCP 8.5. And I've just picked out two of these model runs, and you see very different outcomes for different parts of the US. So for example, California, according to this climate model, we could have a future that is very wet in California and the whole West Coast, or there could be equally plausible a future where California is getting drier and the Pacific Northwest is getting wetter. And these are all plausible outcomes. You can look on the East Coast here, very different amplitude of precipitation increase, depending on, you know, which of these maps you look at. And again, for here we are in Texas, Could have a very dry future or a kind of neutral future in terms of winter time rainfall. So the things that I'd like to now address in this kind of broad brush talk is what causes this range of future outcomes? Is it predictable? Is it trustworthy? Like these are these basic questions that we are confronted with in our climate science. So outline of the talk, and I hope I've piqued your interest with those first couple of slides, and we'll come back to them to try to really pull them apart and understand why they're so different. So first, I'll just cover kind of just in a very broad sense, what are the sources of natural climate variability. Then I'll talk quite a bit about these climate model large ensembles. And then come back to what I think is some of the most interesting things to revisit observed climate trends in light of what we've learned from the models. And then say a few words about model evaluation strategies given this superposition, natural variability and anthropogenic climate change. And then finally come to a summary and outlook. Are we all good? Okay, good. All right. All right, so sources of natural variability. So just sort of classifying them. So the atmosphere itself is a very, very powerful and rich source of variability in the circulation and then the temperature and precipitation that it induces. And then we have another whole class of phenomena of variability that stems from ocean atmosphere coupling, and then the ocean itself can, of course, have variability on longer time scales within the ocean itself. So I'd like to start with the atmosphere. I think we often think about the atmosphere as just being responsible for day-to-day weather or week-to-week weather, but I think that's a very naive point of view. So here I've just illustrated one of my favorite examples, but this happens a lot. So this is an example from February of 2015 when the jet stream had a very high amplitude wave to it, a ridge on the west coast and a trough over the southeast US. And this led to record warmth in the western half of the US and record cold in the eastern half. So these planetary scale meanderings of the jet stream can cause very large scale patterns of climate, you know, on the ground. And this is induced just by atmospheric dynamics. So, of course, we're all familiar with the limited predictability of this kind of chaotic system, typically less than a few weeks for just intrinsic atmospheric variability. And, you know, fundamentally, this predictability is limited because of the very nonlinear nature of the dynamics. And this can be modeled kind of as a random or quasi-random stochastic process as pioneered back in the early 60s by Lorenz and many others since then. And the important thing here is that this is not just happening on, you know, these short time scales, but really there is residual variability on much longer time scales induced just by chaotic motions in the atmosphere. So you have to be very cognizant that if we see multi-decadal changes in our weather patterns, that they're not necessarily induced by, say, slow ocean modes of variability, or by anthropogenic forcing, but they could actually just arise from atmospheric variability on its own. Okay, so that's the atmosphere. Now we can come to this very rich and important set of phenomena that owe their existence to the coupling between the atmosphere and the ocean. So we're all familiar with El Nino Southern Oscillation, mode of variability on interannual timescales. And then these two kind of longer timescale modes, Pacific decadal and Atlantic multi-decadal oscillation in quotes, because we really don't have long enough records to really ascertain that they're truly oscillatory. They may be sort of red noise processes. Really oscillation is, I would say, a misnomer with the data that we have. So for this, the purpose of this talk, again, I'm going to just focus on the limits of predictability. And at this point, we have very much advanced our ability to predict these phenomena, but it's still very limited. So for ENSO, skillful predictions, perhaps up to 2 years in advance, probably a little bit less than that for El Nino. And then for these longer timescale modes of variability, some hint of some skill at out to 5 to 10 years. But again, limited predictability. So that's the upshot. And then finally, just a couple words about ocean processes, intrinsic ocean processes that can lead to variability on longer time scales associated with, for example, the Atlantic thermohaline circulation and deep convection in the Southern Ocean. But I won't say much more about these modes in this talk. So I'd like to step back and just view all of this natural variability as a roll of the dice. And so if pay attention to the predictability time horizon. So for atmospheric motions, weeks, and maybe for some of these longer coupled modes of variability, maybe up to a decade. But that is the predictability time horizon, at least in current state of the art decadal prediction systems. So really, a roll of the dice on timescales longer than the predictability timescale. And this has enormous implications. And I'm just listing 3 of them here, and we'll address them in this talk one by one. So the first is that this introduces a range of outcomes for future climate evolution, so climate model projections. If this natural variability is a roll of the dice, we don't know what we're going to get when we roll the dice. And so there will be inevitably an irreducible range of outcomes. And it very much complicates our ability to evaluate climate models because the real world has given us one roll of the dice, and we don't know, where that sits within if we had, a whole bunch of ability to replay the tape of history, so to speak. And then it definitely presents challenges for attribution of observed climate trends. So I'm going to try to address these issues as we go along. Okay, so that's chapter 1. Chapter 2, begin with an introduction to these climate model large ensembles. And I would say now for the community as a whole that it's really a go-to resource for the study of climate variability and change. And also how climate variability itself may be altered under anthropogenic influence. So some years ago, we led a working group on this topic. And if you're interested in, sort of a whole bunch of applications of these climate model large ensembles, I would point you to this perspective in Nature and Climate Change. So I'd like to, for this talk, just walk you through how these climate model large ensembles are set up. They're sometimes called SMILES, single model initial condition large ensembles. I'm just going to use the term large ensemble as a shorthand. And the one that I'm going to focus on here was run at NCAR using the Community Earth System Model version 1. And I think this has become a really valuable resource for a lot of research that has been going on. So this model is a CMIP class model, meaning it's a global coupled model. This particular model has a spatial resolution of 1 degree nominally in latitude and longitude, and it has representations of the atmosphere, ocean, terrestrial system, and some representation of biology. And this is very typical of these Earth system models. So the way that this particular large ensemble was configured, and there's no one way to do it, but I'll just walk you through how this one project was done. So very typically one runs so-called pre-industrial control run. So you want to get sort of the equilibrated statistics of natural variability under constant pre-industrial forcing. So how long this run goes depends on how, equilibrated the different components in the model are. So here for this project at NCAR, we deemed that the year 400, things were in quasi-equilibrium. So then we began a typical simulation where we then apply the known historical radiative forcings, both natural, for example, volcanic and solar, and anthropogenic, greenhouse gases, anthropogenic aerosols, etc., and then carry this through to the future under the RCP 8.5 radiative forcing scenario. So that's very typical of these kind of CMIP class models. But then what was new for the large ensemble is that we spawned 39 additional simulations. And the way that we chose to do this, given our computational resources and the length of simulation that we wanted to cover, was that on January 1st of 1920, we introduced a tiny perturbation to the atmospheric temperature on the order of the model's round-off error, which is 10 to the minus 14 degree Kelvin. So it's truly the butterfly effect. And then we launched 39 additional simulations just with that tiny perturbation in 1920. So I'm going to use the hammer for the radiative forcing and the butterfly for this tiny initial condition perturbation. So, of course, these simulations start to diverge over time. And the reason that they diverge is simply because the phasing and amplitude of the natural variability differs from one member to another. And this is largely irreducible, or it is irreducible. It's just a feature of the climate system. And it's largely unpredictable. So once we get past this predictability time horizon in the atmosphere and in the coupled ocean atmosphere system, we're then unable to say which way the roll of the dice will go. And then a really important aspect of these large ensembles is this simple arithmetic that you can do. You can be much more sophisticated, but if you have enough ensemble members, then if you average all of them at a given point in time and location, then you are reducing the natural variability because it's phased randomly amongst the different members. And so you can get a reasonably good estimate of the forced response on these local and regional scales. That's something that I think is just a very powerful reason for doing these large ensembles. Otherwise, it's very hard to know if you've really isolated the forced response. Okay, so I think that's the setup on the simulations. Happy to see if there's any questions on that. Okay, so here's what the global mean surface temperature looks like from this CSM1 large ensemble starting in 1850. And then you see member 1 in the black curve going through 2100, and then observations in the red. And then the gray is the spread of showing the spread across all 40 members. So the first thing you have to ask yourself, and this is not guaranteed, I promise you, is that the ensemble spread spans the observed curve. For many climate model large ensembles, this is not the case. CSM1 is quite a good model when it comes to reproducing the trajectory of global mean surface temperature. So given that the gray shading is not very big on the global mean surface temperature, you might ask, what's the point of running large ensembles? We didn't need it in the first place. But the whole point of these large ensembles is to get down to these more local and regional scales. So now I'm going to come back to the figure that I showed at the very beginning of the talk. We're going to look at trends, linear, just fitting, a linear trend, least squares regression trend line to this 50-year period, 2010 to 2060. So we'll look at maps over this time period. Okay, so now I come back to our initial maps that we looked at. So this is the wintertime precipitation trends. I'm going to say over the next 50 years, obviously starting in 2010 isn't quite right, but qualitatively it'll hold for the next 50 years. So this map you have not seen before. So this is the hammer. This is the effect of the radiative forcing, and we obtain this by averaging all 40 members. So this is something that you cannot get from a single simulation with a given model. So here we know that we have, you can do all kinds of Monte Carlo testing, but you can take my word for it, that this is a very good estimate of the anthropogenic influence on wintertime precip. And you can see the increased wetter future for California and the East Coast of the US. And in general, increased precipitation throughout much of North America and drying over Mexico. So I'm going to use this adage, attributed to Mark Twain. So this is what we expect. This is the expectation, that is backed up by, decades of work to understand how the buildup of greenhouse gases will influence precipitation. But what we expect is not necessarily what we will get. And what we will get is just one rendition, according to the physics that is represented in this model. So here is one member of the 40, and we've chosen it based on choosing the member that sits at the 95th percentile of the distribution of the 40 members when averaging the precipitation trend over all of North America. So we have 40 members, the second wettest one, the one that has the second largest increase in precipitation. That's equivalent to the 95th percentile when you have 40 members. So that's the one that has a very wet future for California and a very wet future for the East Coast of North America. So that's what we might get when you roll the dice and you have anthropogenic forcing. And then here is the 5th percentile member. So I'm trying to span the plausible range of outcomes here. And here you can see that, of course, very different outcome of a drier future for much of the South and a wetter future for northern parts of the continent. So these are really different outcomes. And at this point, and on this time scale, we cannot say each is equally plausible because there really isn't any predictability on this 50-year time scale. Okay, so another way of looking at this is in terms of the probability, of having a wetter or drier winter over the next 50 years. So we can take these 40 ensemble members and look at their trends and just count the number at each location that has a wetter future, and then divide by the total number, i.e. 40, and then that gives us the risk or the chance of having a wetter future in the next 50 years. So here is that map, and the yellow and orange colors denote, higher chance of having a wetter future, and then the blue colors denote having a very small chance of a wetter future, i.e. a high chance of a drier future. So it's quite interesting. It's not 100% everywhere. And the northern parts of Canada and Alaska sort of has the highest probability of having a wetter winter, 80 greater than 85% chance over many parts of these regions. And then the only region that is, high chance of having a drier future is Baja California and Mexico. And much of the rest of the country kind of sits in the middle ground. So really this range is, you can't, there's not too much of a, loading of the dice in the middle part of the country, according to this climate model. Okay, and then here's another way to look at these simulations, and this comes from this figure that I'll show comes from that Nature Climate Change paper that I mentioned at the beginning, and it just happened that we had chosen Dallas, Texas as our illustrative location here. So we looked at daily heat extremes in July, so all I know very familiar from this past summer. So we just, in each of these simulations, we took the grid box in which Dallas is contained, and we just marked the days in July on which the historical record high temperature is broken. And I just want to show you how that unfolds in different members. So I call this my barcode plot from the supermarket. And so here I'm just showing you the time series of when these the historical, record temperature is broken in the future from going from 1950 to 2100. So these occurrences are very random across the different members. And that's the whole point, that these extremes, these daily heat extremes are going to unfold, with different pacing and frequency, depending on the roll of the dice of the natural variability. So for example, in terms of frequency, here, you can have one member that has 168 days of record-breaking temperatures, or you could have another member that has more than twice the number of record-breaking days. So there's an enormous range of imprint of natural variability on these daily heat extremes. And then the pacing of when these occur can unfold very, very differently. So for example, in the top graph in that blue box, you get sort of a monotonically accelerating occurrences of temperature extremes, whereas that bottom one is much more punctuated, and it doesn't necessarily increase that much at the end. In fact, the last decade or 5 years has almost no record-breaking heat extremes. So if that happens, it's not a surprise. It's all consistent with this model's representation of the natural variability, that you can have decades or a decade without any heat record-breaking extremes, or you can have lots of decades with record-breaking extremes. It's all within the envelope of the influence from natural. Okay, so now we're going to come to the observational record, and this is really my favorite part. I'm a sort of observational climate diagnostician at heart, and I think these model runs, of course, they're very insightful, but I don't necessarily take them at, face value. But I think they're really helpful for revisiting what we have witnessed in the observational record, and maybe has us ask different questions of the observational data in light of what we have learned from the climate models. Okay, so I'm going to now show you some maps of what really happened in the real world over the last 50 years. So when I wrote this paper, the last 50 years was this time period, 1963 to 2012. I haven't updated it for, the actual last 50 years, but I'm going to expect qualitatively similar results. So this is how the wintertime air temperature changed over this 50-year period. Lots of warming over Canada and Alaska, and relatively muted warming over the western US and Mexico. So that's actually what happened. So here is one of the rolls of the dice from the climate model, simulation number 7. It's a really nice match as these things go to the real world. So you would say I have a really good climate model. It has nailed the observed pattern and amplitude pretty well. But then I can show you, another plausible outcome. This is simulation 25. It doesn't matter what the number is. And that's failure to replicate what the real world did. But that shouldn't bother us, knowing now what we know from the climate model, that there is so much natural variability that we're not necessarily going to expect. You would hope if you run enough ensemble members, one of them will look like the real world, but it doesn't. There can be other possibilities for what could have happened. I think I have a bit of time. I was thinking I would skip this part, but for each one of these, you have to think about as having some superposition of natural contribution to the trend and then an anthropogenically forced component to the trend. So we've done a whole body of work. Well, I'm getting ahead of myself, but to understand why these two simulations are different beyond just saying it's natural variability. And I will get into that in a moment. But then I'm going to show you after that, could another reality have been possible? And that's where I say that the perspective from the climate model large ensemble, sort of demands that we even ask this question. I'm not sure it would have occurred to us, to me anyway, otherwise to ask that. So I'm going to show you that indeed another reality could have been possible. And then this will lead into some remarks about how can we now go about evaluating and comparing climate models given this large range due to natural variability. Okay, so in a nutshell, why these maps are different is due to the atmospheric circulation. And I don't have time to go through any of the details, but I thought I would just show you the upshot. So we have various approaches in the literature to assess what the contribution from circulation effects are on temperature and precipitation. I won't go into any details, but they're in this paper from 2016. So we have a method for accounting for how the circulation changes contributed to these temperature changes. Then we remove that circulation-induced component, and then this is the residual, which we call thermodynamic residual. And now you can see for the observations on the left and then the two climate model simulations, they become much more similar to one another in pattern and magnitude once you remove this natural component of the atmospheric circulation. They're not identical by any means, but they're certainly closer to one another. And then if you look at the ensemble mean from the climate model by average, which is the anthropogenic component, you can see that each of these, the middle row of maps looks much more like the forced component in the models. So it's kind of a technique for actually assessing, for finding the force component that is due to largely due to thermodynamic effects from the radiative forcing. So that's a bit of an aside that I thought it was nice to show these maps. Okay, so now I want to come to number 2. Could another reality have been possible? And I think this is kind of opens up such interesting questions of the real data that we have to work with. So I'm just going to show you one result here. It's based on a really nice body of work that Karen McKinnon, who was a postdoc with me some years ago, developed a methodology for creating kind of a synthetic observationally based large ensemble. So the way, and this is to kind of find, assess what alternate realities could have happened in the real world in analogy with these climate model large ensembles. So I'm not going to go into any detail in the methodology, but the upshot is that we try to remove the force component from the observations. There are various ways to do it. You can detrend, or you can subtract the force component from a climate model, and other ways as well. But once you do that, you can then randomly shuffle the internal variability in time, but you preserve the large-scale spatial patterns of variability. You preserve their amplitude and their autocorrelation properties. And then you can test how well your methodology works by applying it to each member of the large ensemble, and then see if you can replicate the statistical characteristics of the internal variability in the ensemble. And when we do that, we find that actually it's very good, and the methodological error for North American temperature and precip is less than 20%. So I think we have a very good methodology to look at this. Okay, so I'm going to come to maps without belaboring the statistical procedure. So as you saw before, this was the actual observed trend in the wintertime over this 50-year period. And now I will show you the alternate realities based on the observational data. So she ran 1,000 members of this synthetic observational large ensemble. And then we're showing the 95th percentile range. So the map on the left, the lower left, that's the one that is sitting in that 2.5th percentile of the distribution in terms of how much the continent as a whole has warmed. And then the one on the lower right is at that 97.5th percentile. So these are, the ways that the real world could have unfolded. It's not the way that it did, but it could have, according to this methodology, according to if we had a different phasing of the natural variability superimposed upon anthropogenic influence. And it's quite eye-opening. So here is a map I just took from a different paper of the first 30 members of the CSM1 large ensemble. And I've circled for you, it just happened, those two members sitting in the lower right, they look a lot like what you're seeing for these alternate realities based on observations. And we've done, of course, much more robust statistics to really say that this range of outcomes that we see in the model, at least for North American temperature trends, is extremely faithful to the observed statistics. So I think we can place a lot of credence actually into this wide range of outcomes for that the model is predicting. Okay, so now let's see what's next. Yeah, number 3 now, how should we evaluate and compare climate models? So now we're coming full circle. We first looked at large ensembles in models. Then we've come back to look at observations. And now we have to come back and ask, do we trust our models? And this remains very challenging. And I think we can't, it's just a very challenging problem. So I don't have answers by any means, but I have sort of the questions that I ask myself. And sitting at NCAR in the laboratory that develops the CSM model, our section contributes by evaluating the model as it's developed. We're asked to, assess how well is El Nino simulated, and in general, how well is the variability simulated. And we always say, well, we need long enough runs or lots of ensemble members before we can give any kind of, informative answer. So the first thing that I think we have to all ask is, as I said at the beginning, do the observations, whatever you're looking at, a mode of variability or a trend or mean state, do the observations lie within the spread of simulations from a model large ensemble? If your model cannot encompass the observations, then you certainly have model bias. But even if the observations lie within the ensemble spread, if the model has too much variability, then it's very easy to encompass the observations. So that would be kind of a false, positive, if you will. So there's nuances for this to answer this question. Then you have to ask yourself, well, how well does a model simulate natural variability? And this, I think we now really appreciate that it's very challenging to actually assess this from the limited observational record. I have some slides at the end of the talk at the time that's showing that even with 100 years of record, the statistics of Ensemble are very wide ranging from 100 member run to another. So we really are up against some, a rock and a hard place to answer this question. Even more challenging is how well does a model simulate the force response? And this is really hard. And of course, lots of people do very sophisticated detection and attribution work, but I still think it's on these local and regional scales, there's still a lot of work ahead of us to really answer this. And then you want to know if one model differs from another. Does it really have a structurally different response, or is its natural variability different from one model to another? And again, this is very hard to answer. And you really need lots and lots of samples, i.e. lots of simulations with each model to properly be able to compare them. So it's tough, and but it is what we're up against. Okay, and just some references here that have tried to address these questions. Okay, so I think now, oh yeah, I just end with some tools, as Yuko mentioned. Really put a lot of stake in, I think it's so important to share tools with the community. So here's one of them, a package automated analysis tool for analyzing any large ensemble. It doesn't have to be from CSM1. And it helps, I've had so many ideas for papers spawned from looking at the output from this diagnostics package. So I recommend it. You don't have to know at all how it's coded. All you have to do is specify your observations and model data sets, and you get a whole bunch of beautiful plots and metrics for looking at forced and unforced components of climate variability and change. And I was remiss in not saying that Adam Phillips, who's a core member of our climate analysis section, has led the development of this package, and also all the figures that I've been showing are credit to Adam. And then we have a guide to observational climate data sets that the worldwide community has contributed to giving their expert guidance on the strengths, limitations, and applications of climate data sets. And then finally, these large ensembles, we're assembling a large ensemble archive to make it very easy for people to access this, very voluminous amount of model output. And we're expanding it to lots and lots of different variables. So you can go to this webpage to make it's all regridded onto the same grid, so you don't have to do that. It's all hopefully made very, very easy access and use for the community. Okay, so just these 4 bullet points on my summary and outlook. So the top one, we should expect a range of outcomes. I'm not calling it uncertainty. I think that's a very loaded word. We are certain that there's a range of outcomes that is possible at these local and regional scales because of this dual influence of natural variability and anthropogenic climate change. And then second, this range is largely irreducible once you're beyond this predictability time horizon, i.e. decadal and longer timescales. And then this whole beast of natural variability complicates climate model evaluation and attribution of observed trends. And I think it really forces us to, come to grips with that the real world could have unfolded differently from how it did. And then I think these initial condition large ensembles are really providing a lot of new insight and understanding, but, they're not fine scale models. They're not representing a lot of local processes. I think they're best used to look at the large scale. So thanks so much, and I look forward to your questions.
Can I start with one? This is from John Walter, who's online. Asks, how are clouds are El Nino and La Nina cycles predicted?
Yeah. Okay. How are clouds treated? That I really don't feel well qualified to answer, but sure there's the good, bad, and the ugly there in this climate model. But I think as models go, I think it's pretty reasonable. So I know that the coupling between the sea surface temperature and the low cloud radiative feedbacks in the subtropics are underestimated in the CSM1. That is much improved in the CSM2. So that's just one example. As each model generation, is improved, we get better representation of these processes. And so El Nino is very well done in this model, as Yuko has analyzed and many others. And it is, the amplitude is somewhat too strong, but the spatial patterns and asymmetries between El Nino and La Nina are very well represented. But great questions. Thank you. Yeah. That's how you do it in Texas. Okay. I just thought it was important to really emphasize that what you're talking about is predicting from the local regions. There's no doubt about the overall, global warming scenario. Thank you. Absolutely. Yeah. Double emphasize that. Absolutely. And then ask you to maybe say some words about the pros and cons of the 2 ensemble approaches on the single model. Yeah. And the other, the multi. Yeah. On the screen. Yeah. Well, I think, having one simulation from lots of different models, that's what we've been, using from the CMIP archives, or at least the CMIP 5 and CMIP 3 archives. So if you average models together, you hope that, if models are not structurally different, then it's the same as the large ensemble with a single model, and you'll be averaging out the natural variability. But that's really, we know that's not the case. And they all have different mean states and so I think it's very, I'm not sure we're not as incisive in our ability to understand what that multi-model mean represents if we only have one simulation per model. I won't be able to tell you what the forced response on local and regional scales is in any given model if I only have one simulation. So that's why I always come back to that important point. And that's this value of having these large ensembles with lots of different models. Then we can, for the first time, actually compare the forced responses as they evolve. Obviously, by 2100, the forcing will dominate the natural variability. So maybe that's not so much of an issue, but certainly for the next 50 years, that's not the case. So if you want to get the forced response in a given model on these local regional scales, you have to have some way of averaging out the natural variability. I think that's what the value is of these large ensembles. Yeah, but thank you for that question. And yeah, that's why I start out with that global mean temperature curve. You don't need 40 members. I mean, of course, this is simple 1D energy balance model. But, now we're interested in these, where people live and where organisms live. And that's where we have to really worry about the variable.
I wanted to ask about the random variability. The dice are really carefully engineered to be random, right? So they don't have a trend. And you can easily, often there's a flaw in dice. If you really measure them, they aren't really random. I've always thought that what happened with climate models, and tell me if I'm thinking about this wrong, is that not that they're random, but that when you put that very subtle in the noise forcing, it propagates through the system. So that in effect, it's not predictable, but it's not exactly random. It's just not attributable because if you had an infinite, I mean, is it really random or is it's like predestination? Yeah. Is there really a single outcome or is it actually random that if you had an infinitely large computer and infinitely large number of measurements, would it become constrained? Not just we just can't get there.
I guess I use the roll of the dice very metaphorically, obviously. I think, yes, one talks about loading the dice. I think we have to be very careful about separating variability from forced response. And you can shift the whole distribution, and that's kind of loading the dice. But I think the way I think about it is that's the forced response. And then the distribution about the forced response is the natural variability. That can change due to forcing. We know ENSO in many models will get more vigorous as greenhouse gases build up. So the character of the variability can change itself, but it's still internal variability. So that's why I use the term roll of the dice for that. I don't know if anybody else has other perspectives, but that's the way I look at it.
So I had a perspective on that
Okay,
question and then
great.
another question.
Yeah.
So I think you're trying to ask the question essentially, if we knew the system perfectly, would this actually still be irreducible? And I think the work that Lorenz did, the work that Lorenz did in weather models is where chaos theory came from. And I would need to go back and look at it, but I think his main finding is like, even when you know the system perfectly, this is a fundamentally chaotic system. The climate system is fundamentally chaotic. So even if you know it perfectly, you have these predictability limits. So that's my understanding of sort of the state of that knowledge right now. My question comes back to the synthetic observational large ensemble. I think this point that the real world is just one iteration of what could have happened is so important, and I feel like it's so under-recognized in climate science. But I am really struck by the fact that in Karen's work, the observed trend is so close to the edge of that synthetic large ensemble. Like what really happened in the real world is an outlier in the range of what could have happened. And I'm curious, does that tell us anything about the operation of the real world, or is it just a rare events occur?
Yeah, I appreciate your question and thank you. So, I think there is kind of now sort of active research in really questioning whether this class of climate models has correct signal to noise ratio, i.e. the relative amplitude of the forced response versus the natural variability. Each component could be an error and their ratio could be an error. And there's some indication that maybe for a phenomenon like the North Atlantic oscillation, there's some indication that climate models have too much variability and not enough force response. I don't know that that is general. I think it's just a very active area of research. Yeah, it's a good point. For this particular example, that the observed trend looks a lot like the warmest member, but I mean, we've done this more quantitative comparison, and you can't say that the you know, if you plot the standard deviation of trends and compare it to the synthetic, compare it to the standard deviation of trends between the synthetic observational large ensemble and the actual model large ensemble, you cannot refute the null hypothesis that, you know, they come from the same population. So I don't know yet. It's a very good point, and I take your point. But, one nuance here with this observational large ensemble is that we've had to make some assumption of the force response. And that is difficult. And the way that we did it in this paper was we regressed the observations on the ensemble mean, global mean time series from the CSM1 model. So that's this very smooth curve that represents the, you know, radiatively forced component. But it could be that the natural variability happens to be in phase with that in the real world. And that's maybe a tip off of it. That could be just by chance, or it could be this signal to noise paradox issue. Yeah, but it's a really important issue of the world. Yeah. Oh, it's on. Yeah. Mhm.
You really enjoyed the talk. I'll just ask one. You started with a single year and with seasonality. And I wonder, actually I have so many questions about that, but one is related to the last thing you said about greenhouse gases.
Yeah.
Is when you're doing the force response, is that just assuming that the atmosphere is well mixed with respect to greenhouse gases, or do you resolve the seasonal patterns in changes in greenhouse gases, and do those have any impact on these like regional to local scale fluctuations in temperature precipitation?
Yeah, I mean, this model, it's using, you know, these RCP scenario or the SSP scenario. So it has, you know, it's greenhouse gases, ozone, aerosols, biomass burning aerosols, et cetera, et cetera. And they're all seasonally varying to the best of, you know, our ability to measure them. So all of that is, you know, included in the way that the model experiments. So, yeah.
Thank you.
Yeah, thank you.